Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. This is our continuation of the previous module, where in the previous module we discussed the oblique incidence of a uniform plane wave from medium 1 to medium 2. Both medium 1 and medium 2 were assumed to be perfect dielectric. We will continue to assume that one, and we had set up the essential equations, but we did not derive the final expressions for reflection coefficient and transmission coefficient, which is what the goal of this module is, right. So, we begin by looking or recalling this figure that we had drawn earlier. So, there are two media which is separated by z equal to 0 plane. Okay. So, the normal to the interface is basically along the z direction, and we were considering what is called as transverse magnetic polarization, in which the electric fields are given in this particular manner. The magnetic field in associated with electric field E1 would be coming out of this port perpendicularly, and then magnetic field H3 would also be coming out in the same manner perpendicularly. However, the magnetic field for the electric field this is E2, the reflected field is E2. So, for that E2, the magnetic field H2 would be into the board. So, this would be out of board for the case of H1 and H3, whereas H2 will be into the board. The directions are chosen in this particular manner, so that the incident field which is associated with E1 and H1, the components of that particular plane wave, when you do a right angled rotation starting from E1 along H1, if you curl around, then the direction of the propagation of the wave is towards this particular medium, right. So, you have this E1 and H is coming out. So, the curl rule, the right hand curl rule will give you a wave which is propagating in this direction. Similarly, with the assumed E2 direction in this manner and H going into the wave. So, you have this E2 in this manner and H going into this one. So, if you now turn the screw kind of a thing, right hand rule, it will tell you that the wave is propagating away from the interface. Okay. So, the directions E1 and E2 as well as E3 and H3 were all chosen such that the wave is propagating in the incident medium. The incident wave is propagating towards the plus z direction, the transmitted wave is propagating in the plus z direction, whereas the reflected wave is propagating in the minus z direction. Now, with the help of this diagram and the fact that we know boundary conditions mean that tangential electric fields and tangential magnetic field in this case must both be continuous across the interface, you can write down two equations, and with two equations you can actually obtain the ratios of the transmitted electric field amplitude to the incident electric field amplitude. This ratio we will call it as a transmission coefficient. Similarly, you can write down the ratio of the reflected electric field amplitude to the incident electric field amplitude, and we will call this as the reflection coefficient. Okay. There are three electric fields in this problem. You have E1, E2 and E3. However, E1 and H1 are usually fixed by the input conditions, because it is coming from some source and we know what is the power that the incident wave is usually carrying. So, it is necessary or it is sufficient only for us to just calculate the reflection coefficient and the transmission coefficient. The remaining components or the remaining metrics of this problem, such as the reflected power, transmitted power, and if at all there is a power loss, they can all be calculated with the help of these two coefficients. So, we have shown what the components, the tangential components are going to look like. Okay. So, I will not repeat the discussion there, but I am going to write down the tangential electric field here. What I would suggest is that you observe the figure carefully with the angles theta 1, theta 2 and theta 3 taken. We also know, of course, how theta 1 and theta 3 are related. Theta 2, which is the angle of reflection, is basically equal to the angle of incidence from first Snell's law, and this theta 3 and theta 1 are themselves related by the second Snell's law. Now, what we do is, before we write down this set of equations, what we are going to do is to make a small change in the notation. Because we know theta 2 and theta 1 are essentially equal to each other, we are going to rename the angles. We will call this as theta I, meaning that this is the incidence angle, theta r for the reflected angle, which of course is equal to theta I. So, we do not bother about that anymore, and this angle we will call as theta t, t standing for transmitted wave, Okay. So, this is with this new angles that we have written, this is just to avoid theta 1, theta 2 and theta 3 kind of this one, but rather to give you the idea that this is concerned with an incident, reflected and transmitted wave, we have relabeled the angles. Okay. With that, the set of equations, the tangential electric field on region 1, which must be equal to the tangential electric field in region 2 at the boundary surface z equal to 0, and for all values of x turns out to be E1 cos theta 1 plus E2 cos theta 2 must be equal to, or sorry, we will write this as 1 and 2, right. So, we are going to write this as E1 cos theta I plus E2 cos theta I only, because theta r would essentially be equal to theta I, and then I have E3 cos theta t. Okay. If you are worried about what happened to the phase factor, namely this e power minus j k dot r corresponding to the incident wave and reflected wave and transmitted wave, we have shown that for the boundary conditions which have to be valid at the entire z equal to 0 plane and at any x and y point, right, on the plane, we know that these phase factors essentially have to be equal. In fact, equating these phase factors gave us Snell's law. So, I hope where this equation is coming from is very clear. Okay. Now, what about the magnetic field? Well, magnetic field will be all tangential to the interface. Okay. So, that you have H1 minus H2 to be equal to H3. In terms of E, we can write H1 as E1 divided by eta 1, where eta 1 is the medium impedance, eta 1 is square root of mu by epsilon, correct. So, this is square root of mu by epsilon, and H2 is given by E2 divided by eta 1 again. Why eta 1 again? Because both incident and reflected waves are in the same plane. Okay. So, this would be equal to E3 divided by eta 2, that is for the second medium. Okay. Now that we have these equations with us, I will not simplify them further, but I hope that you are able to take this as a small exercise and then show that the ratio, which we will call it as tau Tm. Okay. So, this is tau Tm as the ratio of E3 to E1, okay, and call this as a transmission coefficient. So, this we will call as the transmission coefficient, which is basically the amplitude ratios. Okay. So, you have to keep in mind that this is amplitude ratio, not power ratio, and you can show that this expression can be written as 2 eta 2 cos theta I divided by eta 1 cos theta I plus eta 2 cos theta t. Okay. So, I would encourage you to show that this equation what we have written comes out all right. So, you can check that we have done our this one. So, you have eta 2 cos theta 1. So, hopefully everything checks out correctly and show that this is the equation. Okay. Now, you can also show that the reflection coefficient, which would be the ratio of E2 to E1, which further can be written as E2 by E3 times E3 by E1, and this particular thing we already know, and you can find out E2 by E3 by subtracting these two equations, equation 1 and equation 2, and then adjusting the ratio, adjusting the equations to get this required ratio, and you can show that this is basically given by eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. Okay. Now, observe this equation very carefully. Okay. If I rewrite this equation by saying that this is basically like eta of the second medium corresponding to Tm minus eta of the first medium corresponding to Tm polarization divided by eta 2 of Tm plus eta 1 Tm, what will you observe? You will actually think that this is equivalent to a transmission line whose input characteristic impedance is eta 1 Tm, and it has been terminated in a load, okay, whose impedance is eta 2 Tm, provided you associate this eta 2 Tm as the medium impedance eta 2 times cos theta 2 or rather cos theta theta t, and you identify eta Tm as eta 1 cos theta I. So, depending on the angle of incidence, if you just identify the transverse magnetic impedance, wave impedance or the intrinsic impedance of the second medium to be eta 2 times cos theta t and eta 1 times cos theta I, then the equation that we have written for gamma Tm follow very straightforwardly. It looks like we simply have this as eta 2 Tm. This is like the reflection coefficient of a normally incident wave. Alternatively, this is equivalent of a transmission line in which the characteristic impedance of the terminating or the load impedance of the transmission line is eta 2 Tm, which is basically eta 2 cos theta t, and connected to an infinitely long lossless transmission line having a characteristic impedance of eta 1 Tm. Okay. So, this situation that we have drawn here in the characteristic in the transmission line is exactly equivalent to the plane wave that we have been considering. So, this is a one-to-one correspondence up here. Okay. Now, we will not derive the corresponding equations for the TE polarization. TE polarization is also called as perpendicular polarization. Okay. The reason is very simple, you will see once I draw the picture. As before, we will assume that z equal to 0 separates the two interfaces, medium 1 and medium 2, separates two medium with an interface at z equal to 0. This is your x axis, z axis. Now, as before, you will have an incident wave, you will have a transmitted wave, and then you will have a reflected wave, each of them having their own k1, k2 and k3 vectors. Okay. And instead of the magnetic field being transverse everywhere, we will assume that it is the electric field which is coming out of the plane. So, this would be E1, somewhere here let us say this would be E2, and here this would be E3, and in this case we will assume that all these electric field components associated with the incident, reflected and transmitted waves are all actually coming out of this particular board. Okay. And then you have to adjust the directions of H accordingly. So, if you take the direction of H to be say H1 in this manner, you can show very clearly that if E1 is coming out here and this is your Z axis, so you can see my thumb, then you take this E cross H, then the corresponding vector will be perpendicular and that vector will be the incident K1 vector. Similarly, if my electric field E2 is coming out and I want the wave to move away from the interface, I need to have electric field and the magnetic field in this manner, so that its electric field rotated onto the magnetic field will cause the wave to go away from the interface. Okay. So, the magnetic field will be located in this manner. Of course, in this case the magnetic field associated with this medium will also be located in the same direction as H1. Okay. The equations, I will just write down the tangential boundary conditions or the equations resulting from the boundary conditions of tangential continuity. So, I get E1 plus E2 to be equal to E3 because everywhere this is parallel to the interface, and however, for the magnetic field what we get is minus E1 divided by eta 1 cos theta 1. So, this clearly E1 by eta 1 is basically H1, and you are looking at H1 cos theta 1 or cos theta I in our angle that we were considering, and because this tangential component of H1 is actually along minus x direction, you get a minus sign here. Okay. Apart from that one, the rest is quite simple. So, you have E2 divided by eta 1 cos theta 1, which would be equal to minus E3 divided by eta 2 cos theta I and theta t. Now, without solving the equations, you can already see a similarity between this set of equation and the previous equation that we wrote, right. So, you had E1 cos theta I there, you had E1 divided by eta 1 here. So, if you simply rewrite this equation, instead of that way you write this as E1 divided by eta 1 by cos theta I plus E2 divided by eta 2 divided by cos theta I, which would be equal to minus E3 divided by eta 2 by cos theta t, and associate these denominators with transmission lines with appropriate TE impedances. This is eta 1 TE, which by definition will be equal to eta 1 divided by cos theta I. Okay. And this will be terminated in a load impedance, which is actually the intrinsic impedance or the wave impedance of the second medium, given by eta 2 TE, which is actually equal to the impedance eta 2 divided by cos theta t. Of course, theta I and theta t are still related in the same manner as Snell's law, so there is no change. So what you should understand is that this scenario of TE polarization can be made exactly analogous to a transmission line that we have already seen, with the impedances being eta 1 TE for the main transmission line. That transmission line is terminated in the load whose impedance is eta 2 TE. So from this it is very easy to write down the expression for gamma TE. This would be eta 2 TE minus eta 1 TE divided by eta 2 TE plus eta 1 TE. Okay. You can expand this equation and then show that this is what you actually get if you were to solve this set of equations. We will call this set of equations as 3 and 4, which basically express the boundary condition. So solving for this gamma TE or equivalently tau TE from this set of equations is as simple as writing down the appropriate reflection coefficient expression for the transmission line case. A longer calculation indeed confirms that what we have written is true. Okay. We are most of the times interested in the reflection. Sometimes we are interested in the transmission, but most of the times we are interested in the reflection, because what we are trying in a manner that is similar to the transmission line problems is that if I have a material and if I have another material and I send light from say one material to the other material, obviously if this material intrinsic impedances are mismatched or they are not equal, as in for example air glass interface, right. So glass has a different permittivity or medium impedance eta, whereas air has a different permittivity and hence a different characteristic impedance or different wave impedance or intrinsic impedance. When these two are not same, which of course is true, there will be some amount of power that would be reflected back. Okay. Because the reflected power or the power density is related to the transmitted power density in a straightforward manner, magnitude of gamma square will tell you the fraction of the power that is actually being reflected back. Okay. And this in many cases may not be okay. For example, in many situations you would want most of the light power that is incident onto the glass to actually be absorbed by the material, okay, and then transmitted into the other medium. Okay. You do not want much of a reflection coming from that one. So this is a simple case of say anti-glare glasses. So an anti-glare glass, if you buy and then wear that one, whatever the sunlight that you are going to get would actually be reflected back. So you basically can make the reflection approach as high as possible, or in some cases where you want light to actually enter in the form of a laser cavity, for example, you have to put what is called as anti-reflection coating. Anti-reflection coating minimizes the reflection. Okay. It kind of makes the reflection go to 0, so which means that most of the power is actually transmitted. So whether you are designing for minimizing the reflection or maximizing the reflection, you would deal with fact that you are going to coat materials with different type of materials of certain thickness, then you have your job would be essentially similar to that of matching on a transmission line. So in a transmission line you had one main line, you had another line, and then you put in what is called as a stub line, the one that we studied, which was actually forcing the reflection on the main line to actually be equal to 0. Right. So a concept that is similar can be used here also, and the design of anti-reflection coatings and corresponding anti transmission coatings as the glare thing that we talked about, they all are very important and very practical uses of this set of equations. Okay. However, before going to that, I would like to start off with couple of observations by actually plotting this reflection coefficient. Okay. And I would like to do that one in order to bring out certain very interesting aspects. So we are going to do that. Okay. We will take two different cases, and before we actually go to that one, let me remind you that eta of any medium which is given by square root of mu by epsilon, in our course this would actually be equal to mu naught divided by epsilon naught epsilon r. Okay. And we have already said that square root of mu 0 by epsilon 0 or mu naught by epsilon naught is basically the free space impedance eta 0, which has a value of 377 ohms approximately, and then you have divided by square root of epsilon r. If epsilon r is a real medium, then this epsilon r will actually, square root of epsilon r will actually be equal to refractive index. However, to confuse you, we use the letter n to denote refractive index. Okay. Unfortunately, n and eta have to be distinguished. I hope the context makes it clear, and it is common practice in dealing with optical materials. Okay, when you deal with optical materials or in optics, to use refractive index rather than to use the wave impedance eta. Okay. So, with that in mind, what I wanted to tell you was eta is inversely proportional to refractive index. Okay. So, any medium impedance that you want to obtain, you take the impedance of the free space divided by the appropriate refractive index. Okay. Now, let us write down the expression for gamma Tm, okay, which I will write instead of in the wave impedance or using wave impedance, I will use the refractive index here. And when I use the refractive index, please check this out. This is what the equation is going to look like: n1 cos theta t minus n2 cos theta I, where n is in the refractive index. So, I am going to write this as refractive index form. Okay. So, using refractive index is what I wanted to tell you, divided by n1 cos theta t plus n1, sorry, this is n1 cos theta t plus n2 cos theta I. Okay. Now, Snell's law tells you that n1 sin theta I should be equal to n2 sin theta t, which actually allows me to write cos theta t as 1 minus n1 by n2 square sin square theta I. So, I can rewrite in this expression gamma Tm, the expression can be made to depend only on the angle of incidence theta I, and given n1 and n2 are constants, I will have an expression for the reflection coefficient of the transverse magnetic wave purely in terms of angle of incidence. Now, what I can do is I can actually obtain what I would know kind of a plot or a graph wherein I am going to vary the angle of incidence theta I. What is the acceptable range for theta I? Theta I equal to 0 corresponds to normal incidence, and theta I equals pi by 2, which is basically 90 degrees, right. So, this is 90 degrees, would correspond to what is called as grazing incidence. Okay. Meaning, if this is your interface here, theta I equal to 0 would have the k vector directly in this manner, the electric field will be here and the magnetic field, let us say, will be along perpendicular direction. Okay. However, for the grazing angle, it is the k vector that would be almost along this direction. The electric field vector would be, say, perpendicular or parallel depending on which type of the wave you are considering, and this is how you are going to get. So, you have this interface and then grazing angle is just touching the interface in this manner, and if the electric field is perpendicular, that would correspond to the perpendicular polarization, and that is precisely what we wrote for gamma Tm. I hope that connection is also very clear. Okay. So, this is the range over which the angle theta I can vary from 0 to 90 degrees, and if I plot the magnitude of the reflection coefficient, which is what I am interested, for this kind of a lossless material and having no active gain medium, the maximum reflection coefficient value will be equal to 1. Okay. Now, if you consider two cases, so let us assume that n1, which is the medium of this is the refractive index of the medium 1, and I will assume this n1 to be equal to 1 and n2 equals 2.5. Okay. And then vary the angle of incidence theta I, evaluate the magnitude of this particular expression and then plot it. I can write a simple MATLAB program with just 2-3 values here, or write a simple Excel sheet in order to do that, do this calculation. What you will observe is that when you plot this gamma Tm at t equal to 0, it roughly starts around with a value of 0.43. Please check these numbers. Okay, that will actually give you some facility in using these equations as well. So, it starts at 0.43. What happens is, as you start increasing the angle of incidence at somewhere at a point of 68 degrees approximately, okay, the reflection coefficient actually goes to 0, meaning that there is total transmission at this angle. Okay. The light is basically totally transmitted into the second medium, provided it is purely of Tm polarization. Okay. And we will call this angle as theta b. This is basically called as Brewster's angle, and you can show that this Brewster's angle will actually be given by tan inverse of n2 by n1. Okay. I am not deriving the expression for Brewster's angle, this is there in the references that we have taken, but please verify that for the medium cases that we have considered, n equals 1 and n2 equals 2.5, this angle where this reflection coefficient goes to 0 is roughly 68 degrees. Okay. Then what happens is that the reflection coefficient magnitude keeps increasing and eventually approaches 1, okay, at 90 degrees. Okay. So, this is what you are going to get for Tm equals 1, I mean gamma Tm equals this particular case. How about the transverse electric case? In the transverse electric case, things will be slightly different. Okay. We will do the transverse electric case, but this time we will assume that medium n1 is equal to 1, but n2 equals 1.44, so that this equation starts at 0.2, that is the max amplitude will actually start at 0.2, the reflection coefficient magnitude starts at 0.2 and then very slowly goes up. So, this is for the transverse. I have not drawn the equation nicely, but this is how it actually goes up. So, there is, it does not go to 0, it simply scales up in a very slow manner and then eventually reaches 1 at theta is equal to 90 degrees. Okay. What you have to observe here is that medium 1 was a lower refractive index medium and medium 2 was a higher refractive index medium. Okay. Now, let us switch these two cases, okay, and then consider what would happen for Tm and Te when we let the angle. So, what I will do is I will have the same angle say from 0 to 90 degrees. Okay. I know the maximum value is going to be 1. Okay. So, now I am ready, but this time I am going to assume that n1 is equal to 2.5 and n2 is equal to 1. Okay. So, I am assuming that n1 is basically equal to 2.5. I am assuming that the incident medium has a higher refractive index than the medium, second medium, which has a lower refractive index. In this case, what happens? You look at this, starts off at somewhat close to 0.5 or 0.43, maybe even slightly different than that one, let us not worry about that. However, as you start increasing the angle of incidence, it drops down at some angle 22 degrees, which would correspond to the Brewster angle. The magnitude of Tm will be equal to 0 at this Brewster angle. However, after slight change in the angle, the reflection coefficient suddenly becomes 1 and then remains 1 throughout the rest of the incidence angle. Okay. If you wish to observe this carefully, you can actually decrease the refractive index differences. So, assume that n1 is equal to 1.44 and n2 is equal to 1.0 and then redraw this picture, okay, with same 90, 0 and this 1 that I have, and when you do this case, you start off with some value which I will leave as an exercise, but you will quickly go to 0 at 33 degrees, okay, and then as it starts to increase slightly, at some arbitrary point it is going to suddenly increase and then remain equal to 1, okay. And this angle not very far from this 33 angle, this is actually just about 44 degrees. We will call this as some critical angle, beyond which, so when the angle of incidence is greater than the critical angle, the magnitude of the Tm as well as Te, I have not shown this, but it would also be equal to the same scenario, both will be equal to unity. And this phenomenon is called as total internal reflection, and it figures mainly in guiding light, and it is a very important topic in optics that we are going to talk about next modules. Thank you very much.